So hello and welcome back. In this video we want to talk about the difference between exponential functions and linear functions. So you know that basically linear functions are some functions like a function like f of x is equal to 3x plus 4. You know that this number 4 is your y-intercept, and basically where the function crosses the y-axis, and this number 3 is the slope of the function. So this is your y-intercept and the slope of the function. Now what this y-intercept basically means is it's the value of the function when the input is equal to 0, and that is basically, let's say this is your x and y axes. So you want to draw the graph of this function. You have 1, 2, 3, and 4. So this is y is equal to 4. And so this is basically one point on the graph of the function. And the other point is the slope. And the slope of any linear function is basically your rise over run. That means how your output is changing based on in contrast to your input. For example, this is your slope, and your rise is basically so if this is, let's say, a x and y axis, and let's say on a graph of a function, any function and linear function, you can take any 2 points, and these 2 points, this point, for example, this lower point compared to this upper point, there is some rise in them and there is some run in them. So what is the rise and run? So if you compare the 2 points, you can draw something like a triangle over here, and then this is your run. So you run basically from here up to here this many units to get to this point. To get, for example, let's say this is your x1 and this is your x2. So you have to run from x1 to x2 to get to this point where the x coordinate of this point is x1, the x coordinate of this point is x2. And then again you have to rise this many units from here up to here to get to this point. So let's call this, for example, y1, and let's call this y2. So the y coordinate of this lower point is y1, the y coordinate of this upper point is y2. So the slope of this function is basically the rise of these 2 points divided by the run of the 2 points, and that also sometimes they call it delta y by delta x, and you know that basically delta y is y2 minus y1, changing the y coordinate of the points, and this is delta x is always x2 minus x1, which is change in x. So now let's suppose that since these two distances seem to be the same distance here in this coordinate system, now let's suppose that this is 1 unit here, 1 unit rise, well, I'm sorry, 1 unit run over, and this is 1 unit rise. So that basically means that to get from this point to this point, you have to do 1 unit rise, 1 unit run in the positive x direction, and then 1 unit run in the positive y direction. And so that basically becomes your y2 minus y1 here becomes basically this point minus this point, and the difference is 1 unit. So it's 1 unit here, and the difference between x1 and x2 here is again 1 unit, and so this becomes 1. So the slope of this line is equal to 1. But if you have some other coordinate system and another function, let's say you have this function, and this time the function is basically the slope of the function is steeper, something like this. So something, basically something like this. So now this function is steeper compared to this function. Now if I take any 2 points on the graph of this function, for example this point and this point, so I have to run this many units and I have to rise this many units, and I would assume that this, I could take this, for example, if I take this as 1 unit, this would be then 2 units. So in the case of this function, the slope is basically rise over run, and then your rise is 2 units, your run is 1 unit, so the slope of the function is 2. So that basically tells me that for every increment for every unit increment in the input of the function in x's, I get 2 unit increments in the output of the function, and that is constant throughout the whole function because it's a straight line. It doesn't matter where you take these 2 points, wherever you take them, basically you will get the same ratio, 2 by 1, 2 by 1, and then it just becomes 2. So that basically means that in this function, whenever you add 1 unit change to the input of the function generates 2 units of change in the output of the function. And that's basically the slope of this function. So, but in this function, you can see that wherever you add 1 unit of change to the input of the function is generating only 1 unit of change in the output of the function. So that's basically, this is slope 1, this is slope 2. And this is constant throughout the whole function, and it does not matter what the previous values of the function are. For example, let's say that, for example, in this case, if your function is 3x plus 4, so in this function, if f of x is equal to 3x plus 4, you get a function like this. So 3x plus 4, so this is 1 point on the graph of the function, and then you have a slope of 3, so you run for 1 unit here and then 3 units up, and this becomes the graph of your function. So here basically you can see that you have 3 units, here you have 1 unit. So your rise is 3 units, your run is 1 unit, so 3 divided by 1 is equal to 3, which is basically this slope that we discussed earlier. So now what happens here is that this function, for example, let's say that the output of the function at 0, at x is equal to 0, is equal to what? Is equal to 4. Now if I add 1 unit change to the input of the function, if I calculate f of 1 here, just adding 1 unit, the function is supposed to add 3 units to the output. So adding 3 units to the output, I'm supposed to get a 7 over here, but let's verify if that's true. So f of 1 here is equal to 1 times 3, which is 3 plus 4 is equal to 7. And again, adding 1 unit to the input of the function f of 2, I'm supposed to get 3 units added to this output, so it becomes 10. Again, you can verify that f of 2 is equal to 2 times 3 is equal to 6 plus 4, which is equal to 10. So you can see that this function, there is a constant rate of change in this function, and that's basically why it's called a linear function, because the change is constant. It's just a linear function. It's a straight line. But in exponential functions, the story is completely different. So if you have an exponential function over here, the function is most of the time, for example, we had that function, it was 3 raised to the power x. If you have y is equal to 3 raised to the power x, it's an exponential function. And the graph of this function becomes something like this. So it's very close to the x-axis when x is equal to 0, and then all of a sudden around 1 or 2, the function shoots up like this. Of course, it's not very, I guess around 1 it's 3, so it comes over here and something like this. So this is basically the graph of this function. So you can see that there is no constant rate of change in this function. The output of the function depends on the previous values of the function. I can show you what I mean by that. For example, let me show you the example on page 464, which is about the population of India. Let me get another page here, and we can compare the two things together. So basically, so this was a few facts about and examples about linear functions. And so on the other hand, we have exponential functions like this model over here. And as an example, we can, for example, go through the example that we have on page 464, the population of India. So in India, we have basically the population about 1.25 billion. So the population is 1.25 billion in 2013. And the population is growing, and it is growing at a rate of 1.2% per year, each year. So to get this model, for example, you can basically draw a table like this and see what you get here. So basically, let's call this a function x as or t as time in year. So I have t time in year, and for example, f of t or population p of t as population in billion. So what happens here is in 2013, we know that the population is 1.25 billion. 1.25 billion, and every year it's growing at a rate of 1.2%. So for example, in 2014 the population is 1.25 billion times 1.2. So that basically means that the population is, basically we are adding 20% to the population each year. Or in 2015, the population that we already had the previous year in the beginning of this time interval, so the population that we had was 1.25 into 1.2, and then this population that we had here is growing at the rate of 1.2%, so it's again times 1.2. And so basically I can take this as, for example, at t is equal to 0, I can take this as t is equal to 1, 2, or 3. That means 0 years after 2013, 1 year after 2013, 2 years after 2013. And then you can see that 2 years after 2013, which is 2015, you are multiplying twice by 1.2, or this can be written as 1.25 times 1.2 raised to the second power. Here you can write this as 1.25 times 1.2 raised to the first power. And so you can see that you can see this 2 over here and this 2 over here. So that basically means that in the nth year, in the n years after 2013, then the population is going to be again 1.25 times 1.2 times 1.2 raised to the power n here, because every time we are raising that, we are raising that factor to the power n. So in the nth here it's 1.25 into 1.2 raised to the power n, and this is your basically your p of t, or let's call this t. That is your p of t, which is basically raised to the power t. So that's basically this population. And this population, as you can see, I have to go to the next video, I'm sorry.